Here's a relatively straightforward thermodynamics problem. So this is something that if you're a first year engineering student doing thermodynamics, you might see it in your exam or in your class. So let's read it and then let's try to develop a framework to solve similar kinds of problems in the future. So we have a vessel of volume of 30 liters which contains an ideal gas at a temperature of 0 degrees Celsius. So the first thing I would do is I would just convert the temperature into Kelvin. So that would be 273.15, but let's leave it like that. And this gas is in a vessel. And then after a portion of the gas has been let out, so imagine there's something like a valve, and you release the valve and some of the gas escapes, the pressure of the gas also decreases. So this is something that you would kind of expect, as long as the temperature is maintained constant, which is true. And the question is, find the mass of the released gas. Okay, so find the mass of the released gas, and the gas density under the normal conditions is rho 1.3 grams per liter. So let's write it here like this. And I would also convert this to kilograms per meters cubed because I think this is slightly more useful. So that would be 1.3 times 10 to the minus 3 kg, and 1 liter is 10 to the minus 3 meters cubed. So we can cancel out the 10 to the minus 3's, and we end up with exactly the same thing. So 1.3 kg per meter cubed. Okay, so the way to do those kinds of problems is you want to write down the ideal gas law for the first state, and what I mean by first state is the gas at the beginning, and then you want to write the ideal gas law again for the gas at the end. So at the beginning, we have P times V is equal to mRT. Okay, where the pressure is, well, whatever the pressure is, it's unknown. The volume is 30 liters. Then we have the initial mass of the gas, which we don't know, but we can actually find it out, as m, and then we have r, which is the specific gas constant, and we have t. Okay, now for the second state, so something changed. You released some of the gas from the vessel, and what happened is the pressure dropped. So the new pressure is going to be P minus this delta P. Okay, so if the pressure decreased by 0.78 atmospheres, it means the new pressure is whatever P was minus this 0.78 atmospheres. And this is multiplied by V. So keep in mind that although the mass changed, the volume of the gas is the same. Because gases in general, they always occupy the entire volume they have available, which in this case is 30 liters. And this is equal to the new mass, which is m minus the change in m times r and then times t. The temperature is the same in both cases, right? This is what the question says. So this is kind of an isothermal, it's not really an isothermal process in that sense, because although the temperature is constant, the mass changes, okay? So let's see how we can actually use this to find the mass of the released gas. So basically we just try to find this value here. Okay, so what I'll do is just divide one equation by the other. That's the easiest way to approach this. So we have the following. We have P minus delta P. So I'm going to do equation 2 over equation 1. So I do P minus delta P over P. That's equal to M minus delta M over M. And what we're trying to do is just isolate that delta M by itself and make it the subject of our equation. So let's see how we do this. I would just cross multiply here. So we have M times P minus M times delta P is equal to M times P minus P times delta M. Okay, mass times pressure, that just cancels out on both sides. So, and you cancel out the minuses. So you end up with delta M is equal to M times delta P divided by P, which is fine, but we don't really know all the terms in here. So to begin with, we don't know anything other than the delta P. So we know delta P as 0.78 atmospheres, but we can find the mass because we know the volume and we know the gas density under the normal conditions. So m would just be equal to the density of the gas times the volume. Okay, so that's sorted. The pressure in the denominator can simply be inferred in a way by reading the question a bit more carefully. So what we have is that the gas density under normal conditions is that. So when the problem says normal conditions, that typically means normal atmospheric conditions at sea level. Okay, so that would be just P is 1 atmosphere or just 10 to the power 5 pascals, like this. So now that we know everything, we can put the numbers in here. So we have this mass, which is rho times V, and then we have delta P over that P0 atmospheric pressure. And actually, we can leave the pressure in atmosphere because we have a ratio that we're dealing with. So the mass, or this change in mass, is therefore equal to 1.3. That's the density. And then this is multiplied by 30 liters, which is 30 times 10 to the minus 3 meters cubed, times 0.78 over 1. Okay, so we have 1.3 times 0.78 times 30 times 10 to the minus 3. So that is 0.03 kilograms or 30 grams approximately. Okay, so this is how you do this kind of problem. When you have a state and then something changes to the gas, you write the ideal gas law twice. Most of the time you take a ratio and you can move the terms around and find whatever you're interested in. And that's the end of the question.